Minasan, konnichiwa.
Good afternoon. Dor Israeli from Quantum Machines. Today, I'd like to talk about the future of quantum computing. Well, I studied Japanese a little bit, but it's not sufficient. So from here, I'm going to do my speech in English.
Welcome, everybody. My name is Dor Israeli. After this very embarrassing Japanese introduction, let me introduce myself again in English. I've been working in quantum machines for the past 3 years, and today I am the Director of Technology for the Israeli Quantum Computing Center, which I'm going to talk about. Previously, I've been responsible for the software strategy at Quantum Machines. I've worked with a lot of companies here, and it's very exciting to see a lot of familiar and new faces here at Q2B. So let's begin. Okay, so you must be tired. It's a very hot day. You've been to, 20 presentations so far. So we are going to keep it simple. Firstly, I'm going to introduce Quantum Machines for those of you who don't know who we are, and then I'm going to talk about what we do. That's the second point. The Quantum Orchestration Platform, or QOP. So, これから QOP の意味は
QOP stands for Quantum Orchestration Platform.
And this is the heart of the presentation. I'm going to give you a peek into the future of quantum computing as we see it, using some next-generation projects and futuristic projects that we've been working on, and how do we envision the realization of quantum computers. So let's begin. Quantum Machines is an Israeli-based startup, and everybody in Quantum Machines is either a physicist or a computer scientist or an engineer that has one specific mission in mind. And that mission is to accelerate the realization of quantum computers and quantum computing in order to disrupt all of the different industries. So we want to enable all of the richness of quantum computing that we've talked about in this conference so far. Everybody, again, in the company is an expert in their field. As you can see from the numerous PhDs in this slide, but there are many more. We are already around 170, 160 employees all over the world, mainly in Israel. But we have people in Europe, in the United States, in Canada, and so on. And we already funded and raised around $100 million. We recently merged with Q2B23, which is a very interesting company from Denmark. So we also have offices there. And also we like to boast the number of patents we have. We have more than 60 patents, which is very important and interesting in the quantum computing landscape. Also, we have almost 300 customers all over the world. You can see here also in Japan, in Osaka, in Kyoto, Daigaku, and many more to come. So, before I talk about our technology, I wanted to talk about our mission. So I want to give you a very short glimpse of what we had in the past 12 months. Firstly, we announced, and Sam from NVIDIA is here, so kudos. We announced a collaboration with NVIDIA to co-develop the DGX Quantum, the next generation quantum control solution. And I will talk about that in the presentation. Secondly, a collaboration with Google that I, unfortunately, due to the lack of time, won't talk about in this presentation, where we demonstrated a long-range quantum teleportation. We have a collaboration with Quantware, a very interesting company that does qubits, superconducting transmon qubits, which I'll talk about in a second. A German company called Partec that we have a strategic collaboration with, a very interesting company. I suggest you guys look them up. And I will talk about that shortly, about HPC integration. And lastly, and I will finish the presentation with this, I'm going to talk about the Israeli Quantum Computing Center, a very interesting project because it has a lot of different partners. Okay. Now that we are in Japan, I'm really happy and glad that we have our friends from Toyota Tsusho representing us here in Japan. So thank you very much, Tatsucho. OK, so now you're all familiar with quantum machines, but what do? We do quantum control. We control the qubits. We control the quantum computer. We have a product called Quantum Orchestration Platform that it is the brain of the quantum computer. Why do I say brain? Right? They are the qubits. The qubits are the brains. No? So we have a very interesting analogy that I like. The qubits are like a very strong muscle. They have a very high potential. They can, solve problems in medicine and so on. But like muscles, they need something to send them signals and commands. Do this, do that, right? Without the brain, a muscle cannot even lift one feather, right? This is the quantum processor, the qubits. Again, in the analogy, a muscle. But a muscle must have a brain besides it. And that's the quantum control, which we envision to be on-premise and on cloud. And this is what we do. We do the brains of the quantum computer. We don't do the qubits. We do the brains. And this is how it looks like. This is our main product called OPX+. I'll say the phrase that we really like to say. It enables you to run the most advanced quantum computing algorithms out of the box. Right? It's just one box. It's a one-stop solution using a super intuitive programming language. So it's not an FPGA. We don't give you an FPGA and say, good luck, write assembly for 2 years, right? We give you a box that it's an integrated hardware and software solution. So there's a programming language that I will talk about in a second that we've created called QA that enables you to control the QPU. So here is the quantum stack, right? We have on the one side quantum applications. We just had a presentation about medicine and algo trading, right? And on the other side, we have the qubits, right? The most physical thing. But what do we have in the middle? We have the quantum software, the quantum control software, and the quantum control hardware. And that's what we do. So as you can see here, that's the same OPX that we had before, but it scales, right? You can see several in the same rack. On the one end, inside of it, we have our own proprietary pulse processor. It's a processing unit that we develop, and it enables us to have real-time logic. And on the other end, it connects to the qubits. So we are generic, right? We don't produce the qubits. We enable users to control whatever kinds of qubits you have. If you have transmons or spin qubits, neutral atoms, trapped ions, whatever you have, the OPX can control it and give you a very high-level Pythonic programming language called QA, Q-U-A, QA. It's very intuitive, it's very high-level, it's not assembly, it's not FPGA, and it lets you focus on what you want to do. You want to implement an algorithm. You don't want to nibble around in assembly, right? We also have integration with OpenQASM 3. By the way, I'm on the steering committee of OpenQASM 3, which is the standard of quantum languages, gate-level languages, undermining Qiskit and Bracket and Cirq and so on. So if you're also interested in OpenQASM, please come talk to me. OK, this is not a technical talk, right? I'm not going to give you a demo of QA, but I did want to show you how it looks. QA is a pulse-level language. You can see here we have play and measure. You play a pulse, you measure a pulse, right? Because underneath the qubits, the logical, nice mathematical abstraction, it's physics. It's all pulses. But it's not an AWG. It's not just playing and measuring of pulses. You can also have real-time variables and real-time logic and measurements, right? I can measure a qubit and infer in real time, do real-time state discrimination to understand whether the qubit is excited or in the ground state. And I can use that result in real time, for example, for active reset or for random walk phase estimation, next-generation quantum algorithms, or even to implement QAOA or VQE in real time in the OPX, right? You can see you have if statements, and while you have all of those control flow imperatives in QA. OK, so we've talked about quantum machines. We've talked about what we do, and now let's talk about the next generation projects that we are working on that will shape the future. Mondai Sonoichi.
First problem.
Quantum error correction and hybrid algorithms require real-time classical logic. In order to do error correction, for example, in the surface code, you measure the syndromes, and you need to infer in real time, in coherence time, right? In T1, in less than T1. Hopefully, the sooner the better, you need to infer whether there was any error, and which error, and how should I fix it, right? Minimal weight perfect matching, for example, was talked about in this convention and also in the moonshot convention. So we need to do that. Hybrid algorithms require quantum and classical iterations, right? Quantum and classical, quantum and classical. So there's a lot of latency, the communication latency, that we pay a huge price for it. It would be a shame if we've achieved, quantum advantage and then we lose it for the latency of the communication. So we need some instrument that is able to do the quantum part, but also enables us to do the classical part, which is very intense, for example, in the surface code for error correction, and also very fast. There is no such device today. This is a problem that we face as a community. We all talk here about hybrid algorithms, VQEs, and so on, and error correction, fault tolerant, but there is no device that can do that. So the problem is, how do we enable quantum error correction? How do we upgrade hybrid algorithms? And our solution, which I've mentioned before, is a co-development project with NVIDIA. Together with NVIDIA, we are developing the DGX Quantum. DGX Quantum, as you can see here, is the OPX plus NVIDIA's next generation superchip, the Grace Hopper, combined in a very low latency manner, sub-microsecond, in order to enable real-time classical computation. So you can have, again, GPU power, the state-of-the-art GPU power in real time. You can use that for surface code, for example. This is very exciting. So we are aiming to have a sub-microsecond latency. There is no such thing in the world anywhere, right? This is very interesting. It's more than interesting. It's a must. We must have a solution of this kind in order to advance and have fault-tolerant quantum computers and to utilize the quantum computers as much as we want. So I want to talk about that, right? But I only have like 7 minutes left. So I need to go on, but there are more technical details. So if any one of you have questions, just come afterwards. The second challenge, or the second problem, is that we have HPCs, we have QPUs, but we currently cannot really integrate QPUs into HPCs. People say, yeah, we have ideas about HPC, QC integration, but no one really implemented that, and there are several reasons. So firstly, you can see here in the slides some insights. One, HPC centers have many classical resources. They could have hundreds of thousands or even millions of CPU and GPU cores, right? And they want to also leverage QPUs. And QPUs might also want to leverage the classical resources of the HPC. There is a bidirectional need for integration, but if you think about it, how many QPUs are going to be in one HPC center, right? For example, in Fugaku, how many QPUs are going to be there? Are there going to be 100,000 QPUs as well? No, probably 1, 2, 3, several, right? How do we enable that tight integration into HPC? How do we keep the same software stack and interfaces that we already have today, right? HPC, I don't know how many people here are working in HPCs, but we already have workflows and codes implemented, 10 or 20 or 30 years ago that are working and working fine, and now we just want to integrate a QPU into it. We don't want to reinvent the wheel. So how can we integrate QPUs into HPCs correctly? Again, I don't have much time, so if any one of you have any questions on that, please come and ask me later. But we recently announced Q-Bridge. Q-Bridge is a software integration solution to HPCs. So it's an HPC QC integration solution. As you can see in this diagram, there are many types of users. There are cloud users and on-premise users, all of them using, for example, I've written here Slurm. Slurm is the brains of the HPC. It's the scheduler, for those of you who haven't got the chance to play around with it. And as we have HPC nodes, GPUs, CPUs, and so on, now Q-Bridge enables you to have a quantum node, a quantum partition. You still use the same software. You don't need to reinvent the HPC software stack. You use the same software, but now you have a quantum node. And inside of it, there's the OPX, and then you can leverage the DGX quantum as well. So this is very interesting. There are a lot of non-trivial problems. If any one of you have an HPC center and they want to maybe have remote access to our QPUs, please let me know. And the last problem, because we don't have a lot of time, these two last examples that I gave you, the HPC integration, the GPU integration, and other examples from previous and a presentation given by other people, are the bleeding edge. It's not product grade yet, right? We don't know if that's the direction. No one knows, how do you really do a fault-tolerant quantum computer? No one really knows if surface code is the correct approach, for example, or transmons or neutral atoms are the correct approach. So there's a lot of risk. There's a lot of uncertainty in quantum computers. Who here is willing to bet, his money, his pension, about the future of quantum computing specific technology, right? No one. No one really knows if it's that error correction scheme or this type of VQE and QAOA, right? And this is the reason why there are so many companies like Q-Control and Kedma and so on that try to mitigate errors, right? Or Classic, a good friend of ours, that try to enable more users to access through the cloud. But there's a lot of uncertainty. How do we enable those cutting-edge technologies that are, again, not ready yet for the public? I want to give you access to our bleeding-edge technologies. How do we do that? The way that we've chosen to do that is through the Israeli Quantum Computing Center. We won the government bid to design and build the Israeli Quantum Computing Center, which is, as the name suggests, will be in Israel, right, in Tel Aviv. And it's going to have 3 quantum computers of different modalities: neutral atoms, superconducting, and photonics. Photonics by Orca. Superconducting by our friends Quantware, which I've mentioned in the beginning, and neutral atoms by inflection. And hopefully more to come, maybe annealers, right? And all of those will be integrated into an HPC center that we integrate, again, with Q-Bridge. And all of those will be controlled using the OPX with the DGX quantum. Everything here is going to be accessible through the cloud, even to Japan or to Europe or to the United States, to give people access to our stack, to the low-level QA, the pulse-level QA, to Qiskit and OpenQASM, to DGX Quantum, and so on. And this is the way that we, together with our partners that you can see here on the screen, trying to democratize this bleeding-edge technology. Okay. So I hope that you all got my message on how to accelerate quantum computing and the realization of quantum computers. One, excellency. We must do everything as best as we can. We must have best fidelities, great frequencies and calibrations, the best latencies, right? Everything must be the best as we can. Secondly, innovation. This is something very common both to Japan and to Israel, the need and will to innovate, right? How do we try new ideas, risky ideas maybe? And thirdly, how do we collaborate? We need to collaborate in order to succeed. no one company can do it alone, and that's the reason why we are now looking for power users for the Israeli Center, which will be open soon. So thank you very much. Again, we have a booth here outside, so if any one of you wants to chat, please let me know. Thank you very much.